Hello and welcome back. We are going to be picking up where we left off right here with recursion topic 7.1. So we're just going to go through some more advanced problem sets here. I'm not going to do a ton of live coding for this, just because I already have it pre-coded, and I just would rather go through sort of the general understanding of the flow for this code. Now, when it comes to recursion, the learning objectives haven't changed, right? So you need to be able to implement simple problem solutions, like those mathematical calculations that we just saw, or perhaps going through an array list or an array. You should be able to write these solutions with and without helper functions, and you should be able to look and understand what's the base case and what's the recursive case. Now, all three of these learning objectives, we put a check mark beside them in video topic 7.0. So a lot of this is sort of rounding out the topic of recursion rather than more must understand material, because recursion can be really complicated and hard for our brains to understand. So keep that in mind while going through these examples. Make sure you have a really strong foundation and you understand what these learning objectives are telling you that you need to take away from this topic. The very last bit of this video does talk about when good and bad times are to use recursion. So that part's super pertinent, like it's really important. But some of these more complicated problems, there's two sort of trickier recursive algorithms I'm going to show off, and it's okay if you don't feel like you could reproduce it on your own right now. That's okay. So that's kind of why I'm not going to go into like a 2 hour long video of me showing how to write that code, just because they are a little bit trickier, and it's okay if you don't feel confident in like reproducing that at this moment. Really, what you need to feel confident reproducing is simple mathematical calculations and list traversals and reversing strings and just some of the basic problem solving algorithms that we showed in the last video. So all the previous examples are ones that were solved very easily with a loop. And that's totally cool. And that's sort of our basis, right? That's a very comfortable basis for us to be at. Now, what this does mean, though, is that we haven't really seen a reason for us to solve a problem recursively rather than doing it iteratively, because it was very easy to do iteratively. Now, when a solution to a problem requires lots of recursive calls, the iterative solution becomes way less elegant than a recursive one. And this is what a naturally recursive problem is. And so we're going to look at some naturally recursive problems. We're going to see ones where it's like beautiful and elegant to write it recursively. And it's better to write it recursively. Those are the trickier ones. And then we're going to look at one that is naturally recursive, but way worse to write recursively. All right. Do you remember our friend binary search? It's actually very naturally recursive when we think about it. So our base case, oh, we're missing a word here. I'm going to fix that. Sometimes I was doing so well with few mistakes. All right, so we know that our while loop in our binary search, go back in your old notes, check it out, that our base case, our while loop exited when our high became less than our low, which meant we didn't find our code. We didn't find the value we were looking for. But we had a second way to get out of that while loop, which was if we actually did find our index. If we found the index and we found the target at a given index, we also could break out of our loop. So in this problem, we actually have two base cases. We found it or we didn't. And now our recursive case, we actually have two of those as well, because we either need to recurse on the left half of the array or recurse on the right half of the array. So if our middle point is greater than our target, we need to recurse on our my left and right. It's amazing how bad I am at this. On our left half of our array, we have to recurse on the smaller half of the array. And then if our array midpoint is less than the target, that means our target is greater. So we need to move our low to the mid and make our search continue on the larger half of the array size. Oops. So let's just look at the code. We're not writing it, but we're going to look at it because I do already have it written right here. Here it is. Okay. So I put an array together for us to just look at, just to like have something. We have a target value that absolutely is in the array, and look at how elegant this code is. Now, I don't know if you remember what our iterative solution looked like, but it did not look this elegant. We had lots of variables running around. It did not look like this at all. Now, you'll notice here that I do have a helper method, because as far as the front main method should be concerned, should outdent this. There we go. As far as the outer main method should be concerned, it should just be able to say, here's the array, here's the target value. Is the target value in there or not? However, we want to solve this problem recursively rather than iteratively. So we use a helper method to pass in our initial low, our initial high, our target, and our array. And a reminder that our low and our high at the beginning are just 0 to the end of the array, which is why on line 9, that's what we set here. And instead of having them as variables that we have to constantly reset everywhere, they're built right into the parameters here. Now right here, whoops, we can figure out our mid by doing the appropriate math that we did last time. Here's our 2 base cases. Oh, I have an extra word while right here. And here we have our 2 recursive cases, where in the case of our number needing to be on the bigger side of our array, our midpoint moves, right? Our lowest point becomes where our mid was, and our high doesn't change. And then in our other scenario, our low doesn't change, but our mid does. The only thing that sometimes can be tricky is to remember that our low is an inclusive value, but our high is up to, but not including that value. So when we change to our low, we say +1, but when we change our high value, we don't add the -1. Because we've already checked mid. We've already checked mid. So we don't need to check mid again. So that's why here, since low is inclusive, we do +1. And here, because high is exclusive, we just put mid right there. We don't need to check it again. That's all there is here for this one. I actually do recommend writing this code yourself. So go take your iterative solution and go try and turn it recursive. I did upload this solution, but I recommend trying to do it yourself because it's pretty simple to do. Now, I don't actually have the code, I don't think, for Towers of Hanoi, but it's another naturally recursive problem where what we want to do is we want to move all of the disks that you can see stacked there onto one of the other pegs, but there are rules. You can only move one of those disks at a time, and you can never put a disk on top of a smaller one. So only the top disk can be moved because you can only move one at a time. So it's only the top disk on any of those pegs. And you can never place a disk that is larger on top of a disk that is smaller. And it turns out that this is really easy to do recursively because the rules, if you've ever tried to write out the rules for Towers of Hanoi, like if you try to solve this on paper and really map out what you're doing, you will see that the solution is crazy recursive. Now, here's the actual solution right here. But I'm just going to jump over it for a second because I have, where is it? I should have I don't know. Sometimes I don't know. I should be able to find a great animation of this. Towers of Hanoi animation. And I thought I had one posted, but I guess not. And it doesn't have to be super long. Here it is. This is the animation. We have 1, 2, 3, 4, 5, 6, 7 disks. So disks right here, 7. How many pegs do you want? Let's just change this to be 3 so that it actually matches what we are expecting it to be. And let's just watch the solution play out here. So it tells us the total number of moves is 127. And if we click show moves, it'll go for it. So you can see that we can't place them on the same peg just because of the size issue. And 3 pegs, here's how you do it. This is literally every single time you do it, it's a super monotonous process, but it's like always the same. It's incredibly recursive to solve this problem. It's a great thing to practice understanding recursion because of how recursive this problem is. I strongly recommend that in your head you consider like 3 disks and not do it in your head. Write it out on paper. So 3 disks, 3 pegs, and see what happens and write out each of the steps, and then do it again with 4 disks. And you'll see that in order to do 4 disks, you have to solve it with 3 disks first. And then for 5, you have to solve it for 4, which solves it for 3, which solves it for 2, and so on and so forth. So it's actually an incredibly easy thing to program recursively. Super hard to program iteratively. I don't show that code, but you could Google that code or ask ChatGPT to do it for you, and you would see how hard it is to do recursively, whereas here it is surprisingly simple to do recursively. It's just tricky for us to understand by default, because you'll see right here that there's actually 2 recursive calls happening, 1 and 2, and that can be really tricky for our brains to comprehend without drawing it out first. So just a quick reminder when it comes to recursion, every instance of the method has to be independent from each other. Each has its own set of variables that come through as parameters, which is why in our binary search in the Tower of Hanoi code, we have to pass everything in so that every recursive call has access to the information that it needs. Let's look at a couple of power of recursion examples. These are the tricky ones, and then we're going to see a fun downfall. So first of all, let's consider this idea of subsets, where we're choosing all possible subsets of k numbers from 5 numbers. So it's like 5 choose 3, right? That's like combinations and permutations. 5 choose 3 with no replacement. So choose 3 things from 5 things. Here we're just doing it with numbers to make it easy. Super recursive. We're going to choose k minus 1 things from n minus 1 things. We're going to tack the first thing on, and then we're going to choose k things from n minus 1 things. And we can see here what's happening is first, if we say we're definitely choosing 1, we now need to choose 2 from 4. And if we're definitely choosing 2, we now need to choose 1 from 3. And it can either be this, this, or this. Then we go down to the next solution, where we can ignore the 2s, or the 1s, pardon me, because we've already figured out all the solutions that had a 1 in it. So now here we're going to say, okay, let's pick from picking from 2 solutions, or from, pardon me, we're now going to pick from 3 elements from 4. So we start off by picking 2, and now we need to pick 2 from here. So it could either be 3, 4, 3, 5, or 4, 5. And we can see how we can find all combinations of 3 choose 4. And after we do that, we have to find all combinations of 3 choose 3. And then we're going to find all combinations of 2 choose 3. And you can't do 2 choose 3 because that doesn't make any sense. And we found our base case. Right? So we found our base case. It can be tricky to see, but we did just walk through it, right? So in our top recursion, we went from 3 of 5, then we did 2 of 4, then we did 1 of 3, then we did 0 of 2, and we can stop because we can't take 0 of anything, right? Once we found all of the, like once we picked 3 numbers, we didn't need to pick anymore. First we picked 3, then 2, then 1, then 0. But there was the other way that we had to stop, which was when we couldn't choose 3 of 2. So we had to, let's go back to that picture. So there was first the base case of saying within a level, we need to pick 3 numbers. Once we've picked 1, we need to pick 2 numbers. Once we've picked the second, we need to pick a third number. Once we've picked the third, we need to pick 0 numbers. Stop. Great. That's within a level. But then within each of these levels, like collectively, we had to be able to say, okay, first we're going to pick 3 values within 5. And then we're going to pick 3 values within 4. And then we're going to pick 3 values within 3. And then we're going to pick 3 values within 2. And you can't do that, so we stop. So that's impossible. We stop. And in this scenario, we just sort of print them out as we find them to make it a little bit easier to find the solutions. It's just easier than like returning array lists and stuff like that. So programming, it's a little bit tricky, but the main problem is not directly recursive, right? We're passing a lot of things around here to make this work properly. So if we want to look at the subset code, it looks something like this. It's actually not super long code. We do have a for loop that's going to go through the original list and each time grab us the smaller list, but it's actually really easy to turn this problem into a recursive problem also. All we'd have to do is add another recursive method here. I'm just going to call it outer loop to save myself a headache for a second. We know we're going to need that I value to come in. We know we're going to need our list to come in. What else do we use inside here? We also use current subset inside here, so we're gonna have to pull current subset in. And then all we're gonna do is say, I can spell static. Move this down a little so we can see it. If I is less than the original list dot size, what do we want to do? We want to do all these things, right? Yep. And then we want to call our outer loop on I plus 1 with our original list and our current list, or our current subset, pardon me. Is that what I called it? Yeah. And now all of this, rather than being a for loop, going over each I, this call can just call outer loop starting at start right here, our original list and our current subset. There we go. And now it does the exact same thing. So I've just pulled out that for loop, turned it into an if statement and a recursive call, and now it works beautifully. So super awesome option there as well. This empty return is not great. It's okay in recursive scenarios, but you could also just do this and not have random empty returns that I kind of hate, right? So we can just use if-else statements to avoid having empty random returns, and that's technically better practice. So this is the subset code. Like I said, I'm not going to walk through all this code. We sort of talked through it in words, but I did upload it for anybody who does want to take a look at the code. Okay. Just a final note here, right? When we shrink the list, we have to make sure that we don't actually affect the original list. So this is because they're mutable. So we have to be really careful when it comes to moving all of our data around and making sure that the original list doesn't change so that when we come back up to the top of our recursive stack calls, we're not going to sort of have fudged up our original list, making it impossible to do the next level of subset, right? Because this had 2 for loops in it. We have to be really, really careful of that. This one's even trickier, in my opinion, because this one also uses 2D array lists. So tricky permutations. So we use permutations for lots of things, including subsets, right? We saw a subset permutation scenario. They're very, very similar, but it's also used for things like gaming strategies, traversing mazes, space filling fractals, lots of stuff. So basically, given an array list of integers, we want to generate all possible permutations of an array list. So we're going to do this by producing a list of lists. So we make a 2D array list where we take our original list and then we can go ahead and go through each layer doing very similar steps, where first we say 1 is in the right position, 2 is in the right position, 3 is in the right position, 4, base case. 1 is in the right position, 2 is in the right position, and now these two have to switch. Then we come back up another layer. 1 is in the right position. Well, we're done all the 2s, so we go into the 3s and look at those positions and continue back down. So this, once again, has that double loop scenario that makes it so tricky to look at. Now, what we can see happening here, that's not the number permutations. I named that kind of crappy there. But basically here we were setting 1 and then we had to figure out the 2, 3, 4 permutations. Here we set 2 and we had to figure out the 3, 4 permutations. Here we set 3, we had to figure out the 4 permutations. There's only 1, so we could stop. So we can see how the pattern is starting to build out. After we finished all the 1, like holding 1 in its position and then doing the 2, 3, 4 permutations, we could do it on 2. So here we could say 2, and now let's do the 1, 3, 4 permutations. And then within the 2 1s, we had to figure out the 3, 4 permutations, et cetera, et cetera. I have duplicates here because I'm just kind of dumb, but such things happen. It's okay. Here we're going to do 3, and we have to figure out the 3 permutations, 4 permutations, et cetera. We can sort of start to see how this kind of is an overwhelming task. For our recursive case, we basically want to say for each element in the list, pick an element to be first, and then find all subpermutations of that list. And then add that first element to the subpermutations, and then add them all to the list of solutions. We saw what our base case is, and our base case is when there's only 1 element in the list, there are no permutations, that element alone is the answer. right? That one is super trivial, super easy, no recursion required if there's only one element. One element means that's it. But it would still have to technically be a 2D array list. Now I have this code as well here. It's substantially more tricky to look at because here I've actually removed, like there would have to be additional scenarios here. So this one I do have commented just so that you can understand that here we have 1, 2, 3. We're going to generate all permutations of that list. It gets put in results. We print them all out. This would be a little bit easier to do if we printed as we went. We wouldn't have to worry about backtracking back up our list. This is definitely a tricky, bigger code base. So I strongly recommend only really diving deep into this once you have a really good understanding of the simpler ones. And this is the hardest one that I'm going to show you. And there's literally no expectation that you can walk through this code at this moment. That being said, this is a fantastic interview question that gets asked all the time in interviews, like technical interviews when you're trying to become a developer. Big companies will ask you to find all the permutations of a list. So questions like this definitely do come up, but it's super tricky. And it's just kind of nice to see if you are still sort of trying to figure out a foundation and understand where this can go and where the power of it can be. Okay, so the last thing we want to show off is where this can go wrong. So Fibonacci numbers are super recursive. If you don't know what the Fibonacci sequence is, basically the 0th value and the first value are both 1. And then every value after that is made up of the previous 2 values. So it goes 0 and 1. Technically it goes 0, 1, 1, because 0 plus 1 is 1, and then 1 plus 1 is 2, and then 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and 5 plus 8 is 13. I can go pretty high. 8 plus 13 is 21, 13 plus 21 is 34, 21 plus 34 is 55, and then after that, my brain starts to hurt. But effectively, any given value, Fibonacci of the nth value is going to be equal to Fibonacci of the previous 2 values. This is crazy easy to do recursively. Look at how long this method is. It's so tiny. If n is less than or equal to 1, we're just going to return 1. Otherwise, we're going to return n minus 2, like the recursive calls of the previous 2 values. Like this is crazy simple to look at, and you're like, yeah, okay, that makes sense. Like that's so easy. Let's actually go run this code. This is the only one I'm going to run for you. I have a lot of code in here because I'm going to show the iterative version versus the recursive version, and I'm timing them. But check out the recursive. This is the iterative solution right here. Little long, not terrible, but a little long. This is the recursive solution. Crazy short, super elegant, beautiful to write. It's lovely. Okay, let's run this code. I know how to spell words. Oh, I'm already in the right folder. Okay, let's run this code. I'm so excited. So I'm going to generate the first, how many recursive values did I just do? 0, 1, 1, 2, 3, 5, 8, 13, 21, 55. I can make it up to 10. So let's do n equals 10. We're going to find the 10th Fibonacci number. Let's run this. I'm so excited. Oh, what did I do? Subset. K. K is a thing there. K is a thing there. Oh, I didn't pass K all the way in. I had to pass K in here. Whoops. K and int K. Oh, I should have run that. I'm so sorry. I didn't update that code though on Learn because I didn't mind the single for loop, so it doesn't matter. Sorry about that. That was from the previous example. Let's just look at the Fibonacci. Oh my God. Okay, I will have to fix that code. I made so many mistakes there. I didn't realize I didn't pull all the variables in properly. I'm so annoyed at myself. Okay, doesn't matter. We're not doing that right now. We're looking at something actually fun. Okay, the Fibonacci sequence up to 10 is 55. I just did that on my hand. And we can see both iterative and recursive come up with that solution. And both of them took 0 milliseconds. It was so fast, the computer didn't even care how long it took. Cool. Let's up that. Let's up it to 20. Let's find the first 20. Oops, didn't recompile it. Okay, still 0 milliseconds for both iterative and recursive solutions. Both came out the same value, took no time at all. Cool. Let's go up to 30. Let's find the 30th Fibonacci sequence. You ready? Oh, there's a difference. It's not a big difference, but a difference exists, and that's really important. Iterative Fibonacci of 30 is 832,040 for both. But of course, the recursive one took 6 milliseconds, so it took long enough to register. Let's keep upping this. Let's go to 40. Run. Ooh, once again, the iterative solution took 0 milliseconds. Check out that recursive one, though, 263 milliseconds. But I mean, we're still just talking milliseconds. Like, what's the big deal? That's not even that long. It's like 2 seconds. Like, whatever, right? Not a big deal. Let's do it again. Ooh. Uh-oh. Our iterative solution took 0 milliseconds. Now, there was overflow. I did have overflow. You can see that I have overflow for Fibonacci of 50. That recursive one is not done yet. My computer will crash, so we're gonna have to stop it. Oh, please stop. Okay. So it doesn't finish. It doesn't finish. Let's talk about why. Check out what the Fibonacci of 91 is. It's a big number. Okay, so this is gonna crash. If I try and set this to 91, I'll get overflow again, and that's fine. We can see 0 milliseconds. I got overflow, whatever that was expected. Once again, this is going to run, and this is actually never going to stop. So we're going to stop it on our own again. I'm going to have to hard quit. That recursive solution takes roughly 762,000 years. Yeah. Well, why? That's because, take a look at this tree. For the Fibonacci, for the fifth value in the Fibonacci sequence, this is what we have to calculate. We've calculate 3 and 4. And then for Fibonacci 3, we calculate 1 and 2, and for 2, we calculate 0 and 1. Then on the other side of this tree, for Fibonacci of 4, we have to calculate 2 and 3, but we just did 3 over here. So we actually have to redo this whole calculation right here. Oh, no, where did my mouse go? There it is. Right here, we have to redo it. We had to recalculate the Fibonacci sequence of 1, 2, 3, 4, 5 times. We had to recalculate the Fibonacci sequence of 2, 1, 2, 3 times. As soon as we up this number, this whole tree has even more duplicates, because to do Fibonacci of 6, we have to calculate Fibonacci of 4 on both sides of the tree. And Fibonacci of 4 calculates Fibonacci of 3, and Fibonacci of 5 calculates Fibonacci of 3, and Fibonacci of 6 calculates Fibonacci of 3. And this tree just keeps growing. And it takes so long that even though our solution looks so elegant, it literally wouldn't finish. Like, we'd be dead. Like over 700,000 years, we would be dead. Okay, so what are the takeaways here? First, the simplicity or the complexity, or like how good a piece of code is not just an indication of how nice it is to write it, or how fast it takes to run, or how much space it takes up to run, right? In order to actually analyze a piece of code, we have to understand what's happening. We have to be able to analyze the number of steps or operations that this algorithm is going to take. And we looked at this a little bit when we talked about searching and sorting, and we looked at different sorting algorithms and the number of comparisons that it did. But I mean, check it out here. It really makes a difference. Even though the code was like infinitely shorter to write, it's not feasible code for Fibonacci sequences. And this actually can require a lot of mathematical analysis to understand what's happening, how long it's going to run, why it's going to take that long. So we talk a little bit about that in this course, we do, but really when you hit 2080, that's when you really get to see the power in understanding all of this analysis in a really fun, cool way. I know a lot of people stress about Comp 2080, but it's actually really, really neat. When it comes to solving problems recursively, here are our main takeaways. When we're building a recursive method, we need to answer 2 questions. How can I solve a big problem by solving smaller instances of the same problem? And how can I stop the recursion with a simple, easy base case? One that I know the answer to. This is how I solve every problem in the whole world. When I'm trying to figure out how to renovate my bathroom, I ask myself, okay, I know that at the very end of this, I want a renovated bathroom. How am I going to get there? And I start to break that problem down and I tell myself I need a new sink and I need a new toilet. And then I look at that and I go, okay, well, how do I get a new sink? And I'm like, well, I'm going to have to take the old sink out. How do I take the old sink out? Well, I'm going to take a sledgehammer to it, whatever it might be. How do I get a new toilet? Well, I have to go to the store and pick one out and I have to remove the old toilet. I break all of my problems down into smaller problems until I hit something I know how to do. Sometimes the only thing I know how to do is Google the answer. Sometimes the only thing I know how to do is ask a friend. Sometimes it's like I just need to take a break and have a snack, and that's okay too. I solve all my problems recursively, taking that really big, overwhelming, scary problem, and I keep breaking it down into smaller things until I hit a step that I can handle doing. My whole life works that way. I find it's actually really, really helpful for me. Not everybody thinks that way, but for me personally, I find it immensely helpful. So there are no practice problems that come out of this recursive video, because this recursive video was more just a look into the pitfalls of recursion and the power of recursion. I should have called it pitfalls and power, but I didn't. That's too bad. Missed opportunity. Make sure that you feel comfortable with the basis of recursion. Make sure that you can equate the learning objectives with your understanding of recursion, because it can feel really, really tricky and overwhelming, but it doesn't have to be. And we can definitely break those problems down and make sure that we understand that the takeaways have to be the more simple cases, not these crazy complex ones like permutations and subsets. We will see recursion crop up again when we look at different types of linked lists, which is coming. But until then, this is sort of all that we're going to discuss on recursion. And if there are any questions, as usual, you know where to find, well, I'd say me, but you know where to find your instructor, no matter who it is. And make sure you take lots of time to practice. Thanks.